We are now recording. Okay. So the first part of this talk is this talk divided into two parts. The first is sort of basics, simple extreme value statistics, including extreme value statistics for beginners, which is what I was, say, 5 years ago. All I knew about extreme value statistics was that it existed, that there was a word out there, extreme value statistics, but I didn't know anything about it. And then I had to learn. So whenever you learn something, you discover new stuff. We try to discover new stuff. So that's the talk about in the first part is sort of basic kinds of issues. And the second part we'll talk about is a more sophisticated question, which we'll get to in its time. So it's a very simple question. It's a question you can think of it as a pure math question, but it has applications like all interesting math questions. The very simple question is, I draw n random numbers, say from a Gaussian distribution. So I have my Gaussian random number generator, and I generate a string of 1,000 random numbers, which are distributed according to a Gaussian distribution. How big is the biggest? How likely, I mean, the numbers could be anywhere from -infinity to infinity, of course, because the Gaussian distribution is defined from -infinity to infinity. But say I have a Gaussian distribution with unit variance and zero mean, standard Gaussian distribution. How big is the biggest number of those n numbers of, say, those 1,000 numbers going to be? Is it going to be 3? Is it going to be 30? Is it going to be 1,000? Is it going to be 1,000,000? That's the question. And then before we got on, you can ask the question, why should one care? Why would you, yeah, I mean, other than it's a well-defined mathematical question, but why should one care? And so actually the first person to look at this question in any serious way was a guy named Tippett, a British statistician who was actually got his first degree in physics and then went into statistics and spent his life, interestingly enough, as a statistician for the textile industry, looking at quality, trying to improve the quality of textile manufacturing through statistics. That's what he spent his entire career on, interestingly enough. But so you have an experiment and you have data points, and the question is, you have one point that's out there, and the question is that some error? Is that some, somebody, is it an outlier, or is it just, the largest number? And how are you supposed to decide? Is there any way to know, right? So if the biggest number is supposed to be, say, 3.5, and you get 50, right, for this question of 1,000 random numbers, then the chances are that 50 is legit is extremely, like chance in 10 to the -30. So that obviously there was a mistake there. Somebody wrote down the wrong number because they didn't have computers back then and people entered wrong numbers or things like that. So you want to be able to tell in some reasonable way what's a likely number to see and what numbers are not likely to see. In engineering, it's a real issue. And in fact, most of the work on extreme value statistics came from engineering, because say you're building the drainage system for a city. You have to build sewers and places for the water to go when it rains. Now in Israel, we don't worry about that, and we just let the water go wherever it wants to go, and we don't care. But in other places, they actually do care. They don't like floods, things like that, and they try to plan. And then the question is, again, there's no limit to how big a storm could be, within reason. I mean, the size of an ocean probably is a limit to how large a rainstorm could be, but up to that, that you went to some more reasonable limit. So, and you want to build. So the question is, it's a question of time. If you wait long enough, you're going to get the biggest storm that it could ever be, right? If you wait 20,000 years, but you're building a sewage system or a drainage system. This was last 100 years, say. So the question is, in the next 100 years, what is the largest storm you're likely to see? Right? That's what the engineer needs to know, and then he works on that. Now you should know that that's what they do. And in fact, in Houston, Texas, where a friend of mine lived, they had a big storm and a huge flood, and the mayor said this was the 100-year storm. This was the storm we're only going to get a storm like that once in 100 years. So that's why we didn't design the system for that, because that's, of course, the next year they got another storm that was even bigger, and 2 years later they got a storm which was even bigger than that. So these things are, when engineers tell you things, you have to.
By that time he moved to Boston.
By that time he moved to Boston. But it's the same kind of issue. You're building a building, and it has to be able to withstand the stress of the high winds. And the question is how large a stress is that building likely to see over the lifetime of the building, right? So this is an important, critical question in engineering. I got into this business writing a paper about the immune system. In the immune system, there are these things called T cells, which are responsible for identifying, attackers and stuff like that. And the idea is that you want this T cells to be very attractive to proteins, right? Because you want them to identify, quote unquote, a protein and latch onto it, an antigen, and therefore start an immune response. But you don't want it to respond to your own body. That would be very bad. Those are called self-immune diseases, and those create all kinds of problems. So by the way the body works, at least the theory is that T cells undergo a training session when they're made. They're manufactured randomly. The body manufactures random strings of T cells with random codes on them, and they test them. And the way they test them against the body's own short protein things called peptides. And now you can't test them against them all because that would take, there are too many of them and take too long. So you test them against a sample, a large sample. And if they react strongly to any of the body's peptides, then you throw it out. That's the idea. And then if you're doing a model of this, we wanted to know, well, how reactive are the ones that survive? How reactive are they at that point? What is the distribution of reactivity, given that they only were tested against 10,000 peptides and not against the full 10 to the 6 or 7 peptides in the human body, something like that. So again, the question was, how big is the strength of interactions around the number, and how big is it for the 10,000 peptides you test against? What's the most reactive one going to be? In finance, this is a critical question as well. There's things called options, where you put down money and you have the right now to buy a stock, and you're going to exercise that option only if the price goes below some point, say. Or you have the opposite question, and you make money only if the price goes above. You have the ability to buy the stock, but it only pays to buy the stock if it goes above $30 a share or whatever within the 2 months of the option. And so the question is, when you're you're selling this option to somebody, you want to know, what is the chance that you're going to lose money on this deal? What is the chance that the price is going to go above $30 within the next 2 months? Assuming that the prices the log of the price is a Gaussian random number, which is the standard assumption, which one can question whether that assumption is valid, but that's what they do in practice. And so you have to know what is the largest price value that you're going to actually achieve over the time frame of the option. And then another one with climate, there's a claim out there that, because of global warming and all that good stuff, that weather events are getting more extreme, that not only is the world getting hotter on average, but really the big effect is that the largest, that there are going to be huge swings in temperature. It's going to get very cold, it's going to get very hot. And now you want to look at the data and understand, again, like the outlier question, is it the fact that we got this huge storm last week, well, is there any meaning to that? Is that something that the normal course of events without global warming, is that something we should expect or not expect? And so again, the question of how big is big enters into that whole.
But David, of course, as you said, actually, that this only makes sense if you know the underlying distribution.
Of course.
And of course, the only way we know the underlying distribution is by looking at some kind of
looking at the existing
average events.
Right. or no, looking at the past history, right? We have the whatever history we have. Yeah, I mean, but that's how these questions get asked. I mean, you know, so we're done with the philosophy and the right. That was just to convince you that you know there are reasons that people ask these questions or people think about these issues. So now let's go and actually look at the math. So the math is at this level's very simple. The answer is obvious, right? If you have IID variables, which is the independent, identically distributed variables, i.e. you're drawing n numbers from the same distribution. You have some random number generator, either a Gaussian random number generator, Poisson random number generator, uniform random number generator, whatever your favorite random number generator is. You generate n numbers like that, and you want to know what the biggest one you generate, what the biggest one is going to be. Well, okay. So the numbers are drawn from some underlying distribution P, right? And what's the critical tool is the cumulative distribution function, which is the integral of P from -infinity to x. That's the cumulative distribution function. It's the probability that the number is less than x, right? So that goes between 0 and 1. And given G, we can formulate the answer because the CDF, the cumulative distribution function of the max of the numbers, which I'm going to call capital G instead of small g. Small g is the CDF of the underlying distribution, and capital G is the CDF of the maximum, and then therefore it has a subscript n because it depends on n, how many numbers we looked at, right? Which is the probability that the max of the numbers is less than z, right? Well, if the max is less than z, that means that all the numbers had to be less than z, because if any number was bigger than z, it wouldn't be z wouldn't be the max, right? So therefore, since the probability that any given number is less than z is small g of z, and all n numbers have to do that, it's just g of z to the nth power. End of story. We have solved the problem completely. We can all go home. But okay. Now the question is so this is the simple part. This was written down by this guy Tippett in 1927. As Tippett actually, when he started his master's degree, that was his first paper. And what he did is he took the normal distribution, Gaussian random numbers, and just made up tables for what is the distribution for 2 random numbers, for 3 random numbers, the maximum of 5 random numbers, 10, 15, blah, blah, just tables and tables. Now, that's of course trivial. We can all go to MATLAB and generate that ourselves in 10 minutes. What's interesting, it was a little harder back in 1927 because you didn't have MATLAB and you didn't have computers. All you had is books of tables of integrals and things like that and a slide rule, and that's it. So it's with a non-trivial task back in the day. So we should appreciate, there was a lot of hard work. And then he had all this data, and then I guess he started talking to a real mathematician, Ronald Fisher, who was like the founder of mathematical biology. And he said, okay, ask the following question: what happens when n is large? Because he looked at the graphs and said, the shape of the distribution seems to be converging when n gets big to some shape. What is that shape? And so that's that's a non-trivial question. The question of what the exact answer is trivial, but to approximate that for large n, to understand what happens for large n is a non-trivial, is less trivial, at least. Now, large n, if we have a lot of random numbers, then we expect that the largest number will be rather big. And the bigger n is, the bigger it is, because we have more chances to get a big number, right? So large n is large z. That's the thing you need to keep in mind for this whole talk, is large n means large z. All right, so we need to evaluate g of z to the nth power for n large, and when z is large. All right, okay. So now when z is large, g of z is the it's an earth. It's related to an earth because it's one half plus one half earth with the error function, which is the integral of the Gaussian. And for large z, that goes to 1 when z goes to infinity and approaches it like a Gaussian. So it's 1 minus e to the minus z squared over 2 divided by the square root of 2 pi z. Because if you take a derivative of that with z, the primary contribution for large z is when you take the derivative of the exponent, and that cancels this, then you get a z, which cancels the z in the denominator, and you get your Gaussian. So the derivative of g has to be p, so that's fine. All right, now we take that to the nth power, so we have 1 minus a small number to the nth power, so that's an exponential, right? And so what we get is e to the minus n, e to the minus z squared over 2 over z squared. Yeah.
Doesn't depend on the variance.
I'm assuming standard Gaussian, and the numbers, otherwise everything scales. Right. This is, think about everything divided by sigma. Right. So I make sigma 1. Just because why have useless symbols floating around. Okay. We can eliminate now, the trick is we can eliminate n from this expression, right? But if we shift z. So we're going to say z is some number a, which depends on n, plus by. So we're going to go shift variables from z to y, right? By putting in this shift. And the idea being that by, the fluctuations are small, hopefully, right? That we have some answer plus small, relatively small fluctuations around some answer. And then the question is first, what is a? What is the answer? So if we define a by the following expression, that if n times e to the minus a squared over 2, a squared 2 pi, set that equal to 1, that defines a. Right now, the solution of that is exactly solvable in terms of a special mathematical function called the Lambda function, it turns out. Or you can solve that numerically, whatever you want. The key is that a is of order. The first thing you need to first take home message is that a is of order square root of 2 log n, right? Because a squared, therefore, is 2 log n. A squared over 2 is log n. E to the minus log a, e to the minus log n is 1 over n, cancels the n. And then you get logarithmic corrections and log corrections and log corrections and all kinds of horrible, messy things. Or it has an exact answer called the Lambda function if you know what the Lambda function is. All right. But in any case, that defines a. So now basically that's what that says is basically you want that the probability of that your z has to be big enough so the probability left over is basically 1 over n. Because if you're picking n numbers and the probability of getting a number bigger than that is 1 over n, then you have basically this order 1 probability that's what sets the scale with a. All right, and then okay. Now, so you plug that in, and now you expand the z squared, so you get a z squared is a squared plus 2aby. So now you have e to the minus aby. That's gn approximately. All right, and now if you define b to be 1 over a, what we have is a very simple distribution: e to the minus y. And now that distribution has been called nowadays, it's called the Gumbel distribution, which is a horrible historical injustice because it should be called the Fisher-Tibbett distribution because they're the ones who discovered it. What happened is that in the 1950s or so, there was an engineer called Gumbel who wrote a whole book about extreme value statistics, and that sold that idea to the engineers, and so somehow the distribution got to be called by him. But it really was discovered by Fisher and Tibbett in 1928. All right. So, and the idea is that A is large, but large is now in scare quotes because A is only the square root of log n. Now, log n is not, even if n is a big number, say 1,000 or 1,000,000, right? Even if it's 1,000,000, then log n is 12 or something, I don't know. So 13. And square root of 13 is 3.5, right? So the square root of log n is not a big number, even if n is a big number, and that's where the problems start. That's why, as we'll see, that's the problem. And now B, B is 1 over A, so A is large, quote unquote. B is small, quote unquote. So we have a narrow distribution around A. So we now know how big the numbers are supposed to be. They're going to be of size A, right? With a width that's of the distribution plus or minus 1 over A. Okay. This way. Okay. So how does this look like? So here, what I did is I just plotted the exact answer because I have MATLAB and I don't have to work very hard. And this, the red curve, is our Gumbel distribution. All right. Now you see that it's not crazy. It's you know, got the right. A is pretty good. The placement is right. The width isn't great. It's the right order of magnitude, but it's not great. Not very impressive. A is, you see, not very big. It's 2.375 for 100 random numbers. Right? So it's big, but only among friends. But the point is that it's very hard. The lesson is that you're never going to see a very large number. You draw Gaussian random numbers, right? You know that you're going to see 3, maybe, if you draw a lot of numbers, but you're never going to see 20 out of a standard Gaussian random number generator. It's impossible, right? That's what you need to know. Okay. So, given that it's not so good, the question is, can you do better? So in fact, Fisher and Tippett in their original paper in 1928 said that, hey, this doesn't work very well, right? Because they had all the data that Tippett had generated, and they plotted it up, and they had this wonderful theory that said that this worked. And yet they said, well, yeah, it works in principle, but it doesn't work very well in practice. And they tried to fudge a way to make it work better, and they didn't really succeed. But you can do better. Because all you have to do is expand to higher order in Y. But that's not what they did. At first, I don't know why they didn't do that, because it's an obvious idea, but they didn't do that. But if you do that, just expand to one more order in Y, right? You get a distribution which is not a Gumbel distribution, it's a Gumbel distribution plus a correction. It's easy to work it out. It's not pretty, so I'm not going to write it down, but you can do it. If you do that, you see that you do, even for n of 100, you do much better. And so that'd be with the first correction, that's this green line here. And you see that it's much, much better than the, right? Now, however, mathematicians, however, never, Fisher was bothered by this, and Tippett was bothered because Tippett was a practical man. Mathematicians are not bothered. So, you ask a mathematician, what is the limit of the extreme value statistics for your Gaussian random number? And they'll say, it's Gumbel, and the position is square root of 2 log n, and then they're happy because that's true in the limit when n goes to infinity. But you're never going to get there. So, so this simple kind of idea works, and if you want, you can calculate second order correction and a third order correction.
Expansion asymptotic.
Yeah, it's an asymptotic series, sure.
This also is very reminiscent of normalization.
Yeah. So in fact, you can say, and people have said, that in fact Fisher and Tippett basically invented the renormalization group in their first paper, in that paper, because what they said, and that's how they get it. Or an alternate way of thinking about it is just like it's like essential limit theorem, except instead of sums, because a sum you can think of as a essential limit problem, as a renormalization problem. So if you have a sum of a million variables, you can think of that as a sum of 1,000 sums, right? And each sum is a random number. And if there's a limit distribution, then that has to be the same limit distribution. So it's a limiting distribution, you get it by breaking the sum up into 1,000 sums of 1,000 numbers. Here, the maximum of the million numbers is the maximum of 1,000 numbers, each of which is the maximum of those 1,000 numbers. And you have to get a, so yes, and so you can talk about it in renormalization language. And in fact, that's the first person who really spent time calculating this correction, did it that way and worked really hard. Didn't know, however, and that's wonderful, you can think of it that way. to do Taylor expansions is something that everybody can do. To do renormalization group, you have to, spend 3 pages doing it instead of 1 line. So, takes your, but it's not so deep. It's not as deep as renormalization group, right? Okay. And it turns out, right, that Gumbel, our friend Gumbel here, is the asymptotic distribution, not only for the Gaussian, but for an entire family of distributions. For any distribution which has an exponential type of tail, so it could be e to the minus x, e to the minus x squared, e to the minus x cubed, e to the minus square root of x, any distribution with an exponential tail, the extreme value statistics for that is our same Gumbel. How do you show that? Well, this is what Fisher and Tibbett did, but they did it their way, and I'm doing it my way, right? And it's a very simple argument again. All we need to do is take G, define capital L, L for logarithm, is minus the log of G. That's what you have to do, all right? In terms of which, you can write down G of n exactly again as e to the minus n, e to the minus L. Right? Because we know what we're looking for. We're looking for Gumbel, which is e to the minus L, e to the minus x, right? So the point is that now you Taylor expand L of z, right? You substitute z equals a plus by, right? You do that, you get e to the minus n, e to the minus L of a minus L prime of a, by, dot, 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 right? Now you define a by n e to the minus L of a as 1, right? You define b as 1 over L prime, and what do you have left? A Gumbel. So that's how you get a Gumbel. No work. I mean, 1 line, literally 1 line. And okay, and the only condition is this. I mean, this seems to work for all distributions. Where did the exponential tail come in? Well, okay. The condition is that b has to be small. That's the condition. B has to be much, much smaller than a. Right? Otherwise, this expansion, the next term, there's no reason to stop here. The only reason to stop here is if by is already a small term. Right? So y is supposed to be order 1, b has to be therefore small compared to a. All right. So for a generalized exponential, you have e to the minus log g is e to the b minus alpha. This is an exponent. Sorry about that. E to the minus x over x naught to the alpha, and so L is x over x naught to the alpha. A therefore is x naught log n to the 1 over alpha. B is x naught log n to the 1 minus alpha over alpha, and that's much, much less than a for all these exponential distributions. Okay, and then you can get higher order terms by just continuing the Taylor expansion as many terms as you feel like. And with Mathematica, you can do 4, 5, 6, 7, 8, 9 terms, whatever you feel like. Okay, now you should know also that for an exponential distribution, log g is asymptotically linear. So there's really nothing to expand. So this process works fantastic for one example, things with an exponential tail. And that will be important to us in a few minutes, but it's something that you should know. Whereas, just the Gumbel answer by itself is for a Gaussian. For an exponential, it's spot on. Okay? Now, it doesn't work. This, as I said, there are distributions for this which doesn't work. For example, things with power law tails. So you have that p, for example, is x to the minus 1 minus mu. Log of g is therefore x to the minus mu. Log L of z is minus mu log z. If you go through the exercise, you see that an is n to the 1 over mu, and bn is an over mu. Mu is a number 1, 2, 3, 4, 5, 6. And therefore, B and A are the exact same size, and you can't stop. So this extension doesn't work. All right. Now, however, you can just change variables, right? To do change variables, and it's a story for the PDF because you get the Jacobian. To change variables for the CDF is absolutely trivial. You just plug it in. You do nothing. right? So let's change variables such that the tail we have a distribution with a parallel tail. We can easily say that that's a distribution with an exponential tail in another variable, in the variable log x. So we define W is just log x. Then GW is 1 minus e to the minus mu W, right? And now we have an exponential distribution. And this process, our game works, and we get Gumbel spot on, right? For the exponential distribution, and we calculate A is log n, and B is order 1. So in fact, B is much, much smaller than A, and this works great. And when you plug that back in, so you take the Gumbel in W, this is a Gumbel in W, you plug in what W is, you get this distribution. Now that has a name, it's called the Frichet distribution. And so it turns out that the extreme value statistics for parallel distributions is not Gumbel asymptotically, it's Frichet. This e to the minus z to the minus power. That's a Frichet distribution, and we have proven that for parallel distributions, you get Frichet and not Gumbel, because the process of getting Gumbel doesn't converge, but this does. So, but the point is that Mr. Frichet is only the same as Mr. Gumbel in disguise. It's a Frichet in X is a Gumbel in Y, in W. Now, this is a trivial observation. I have never seen it in print before we wrote it down. I don't know why. This is not how Mr. With the fancy renormalization group, this is not what Mr. Fisher and Tibbet did, right? This is, I think, is a much easier thing to say there's really only Gumbel. You just have to find the right variable. And okay. And so the point is now the scaling Z goes like n to the 1 over mu. So if you have a parallel distribution, this tells you how big the number is going, how the biggest number scales with n. All right, and how does that work? Wow. So there's Mr. Frichet, there's the exact results, and there's absolutely no difference between them for 100 variables. Because it's really just an exponential distribution in height. And for exponential distributions, Gumbel's works just fine. All right, the same is true if you have a distribution with a bounded support. All right, i.e. that the numbers are between 0 and 1 or 0 and 2, right? And there are no numbers bigger than 2. All right. But it has to be the case that the G goes like 1 minus xm, the biggest x, minus x to a power. If it goes exponentially, then in fact it's Gumbel. But if it just goes like a parallel to the limiting value, if the CDF goes like parallel to the limiting value, then this is third class. You again change variables to W, which is log of xm minus x. You get an exponential distribution in W. You take the same game. You get this distribution. And this distribution has a name too. This is called the Weibull distribution. And now again, Weibull is nothing but Gumbel in disguise. So those are the three things that's what Fisher and Tibbet discovered, that there are three classes of distributions, and it's always either one of the three. A distribution, the EVS statistics are either Gumbel or Frichet or Weibull. You ask me, they're always Gumbel in the right variable. So again, all right. Okay. And I was supposed to have a graph of how well Gumbel worked too. Got lost. But so by the Frichet, so the Weibull works perfectly well too.
So the only assumption is about this having random independent variables.
Yes, right.
And as long as this is true, then that's
right. And then the question is what happens.
You don't have to be the Gaussian.
No, I just did it for every distribution under the sun.
Yeah.
For your very odds.
Yes.
Right. Okay. In fact, this solves our previous problem that Gumbel didn't work very well. But Gumbel works well for exponential distributions. Well, we just learned that even parallel distributions are exponential distributions in the correct variable. All distributions are exponential distributions in the right variable. So this is a general strategy now. Take any distribution that you want, Gaussian, e to the minus x to the fourth, e to the square root minus square root of x, whatever you want, right? Change variables to an exponential distribution, and life will be much better, right? And in fact, the fact that you get Gumbel and then you get Frichet and viable are just extreme cases of that. So, i.e., if you have an exponential distribution and x, like with a power alpha, and alpha goes to infinity, that approaches a bounded distribution. So the problem with an e to the minus x to the fourth distribution is it's essentially bounded. It's almost bounded, right? And so the trick that worked for a bounded distribution, namely changing variables, works for this as well. Similarly, when alpha goes to 0, it's a power law distribution, and our trick that worked for power law distributions, namely, will work for this as well. And if you do that, you get amazingly nice results. This is for when alpha is a fifth. If you see, you do the standard treatment of Gumbel, because it is Gumbel eventually. If n is 10 to the 20th or something like that, it's Gumbel, right? But for n of 5,000, it's completely wrong, completely wrong, right? And yet you do our trick, it is Gumbel in the right variable, you change back and you get that. Similarly, this is for alpha 5, the same story. The blue is terrible. The red is when you do our little trick. And this works for the whole, since it works for the extreme cases of Frichet and Weibull, it works everywhere. So that's our little contribution to the solved problem of independent variables. And now we move on to the real new stuff. And the real new stuff is correlated variables, but that's not true. That's all right. Because in real life, especially for physicists, numbers don't come out of random number generators. That's for mathematicians. Numbers come out of some dynamical process. There's some physics problem, and you're looking at the numbers that come out of whatever measuring device is producing your numbers. It's a process.
Even random number generators.
That's also true, right? Yeah, yes. Okay. Now, so the question is, how do things change when the numbers are correlated? All right. First, the most important question is Gumbel still true? Because if Gumbel is not true, then we're totally lost. We're totally at sea. And even if it's Gumbel, how do the scaling parameters, an and bn, how do they change? All right. Now, major progress was made on this 2 years ago by Majumdar, Pal, and Scher. In fact, it was made by them about 10 years ago, but they wrote it up in a conference proceeding, and they never published it, and they finally got around to publishing it 8 years later. I don't know what the story behind that is, but that's the case. And so you need, in order to discuss correlated variables, you have to tell us where the numbers come from. What process generated the numbers? So what they looked at is the simplest possible process of generating random numbers, one of the simplest, which is the what's called the Ornstein-Uhlenbeck process, which is just an overdamped harmonic oscillator driven by noise. So x dot equals minus x, so it's an overdamped harmonic oscillator plus noise, plus standard white Gaussian noise. All right, the equilibrium, yeah, any question? Somebody had a question? All right, so the equilibrium distribution for this is trivial to work out. It's just a Gaussian. And you have a harmonic oscillator driven by noise. The equilibrium distribution of the numbers is Gaussian. Fine. So the numbers we're looking at that are coming out of our process are in fact Gaussian random numbers. The only problem is they're correlated. If we take the numbers, throw them all up, and let them fall back to the ground, then you know what we get. All right. But so what happens now? So Majumdar and friends, what they did is they solved this problem. They mapped the extreme value problem for x of t to a first passage problem. First passage problem is a class of problems where you ask, what is the probability given that it can't cross over a boundary, that there are limits. All right. So because if you look at G, the CDF, right, of Z, which is the probability that the max is less than Z, right? That's the probability that X never crossed Z again, right? I have this process. Here's my X of t, right? And if I want the probability that the maximum is less than Z, that means it can't ever cross Z again. right? So it's just a survival probability. It's a probability that this path never crossed. That's the first passage problem. It's the integral from minus infinity to z of p, where p satisfies the Fokker-Planck equation, right? With a linear force. All right, and p, the boundary condition that p of z is an absorbing wall at z. So all we have to do is solve that Fokker-Planck equation.
So just to make sure that I understand this.
Yeah.
So the correlation is because of the potential, the harmonic potential.
Right, because you don't use memory.
It's not just uncorrelated noise, but
Right,
it's
it's
harmonic
noise,
potential, and that's why
Right.
variables are correlated by the fact.
Right. This is right. This is okay. Now P is and so also G have solutions in terms of the eigenvalues and the eigenfunctions. The way you can solve a Fokker-Planck equation the same way we solve time-dependent Schrodinger equations. You break it up into time and space, and you get eigenfunctions and eigenvalues, and it's either minus lambda t times the eigenfunction, right? And now in long times, G, therefore P, and therefore G is dominated by the lowest magnitude eigenvalue. All the eigenvalue, there's one zero eigenvalue, which is the equilibrium state, and all the other eigenvalues are negative. And the long time behavior of how you approach equilibrium is determined by the lowest magnitude eigenvalue, the smallest negative eigenvalue, right? The one with the smallest magnitude, right? Since when z goes to infinity, the lowest eigenvalue is 0. The lowest so the lowest eigenvalue. Yeah, they're all negative. That lowest, smallest in the magnitude sense.
But then it diverges a long time.
But no, wait. So when z goes to infinity, right, the lowest eigenvalue is 0. Now, when I put in a wall, the lowest eigenvalue of the harmonic oscillator, say the harmonic oscillator with a wall, it raises the energy slightly, right? So therefore, it's slightly different than 0. It's exponentially different than 0. The lowest eigenvalue is non-zero, and therefore, long times G is 1 minus A of z, e to the minus t lambda naught of z, where lambda naught of z goes to 0 as z goes to infinity. That's okay. All right. Also, you can show that A of z goes to 1 for large z. For large z, lambda naught, in fact, goes to 0 like that.
So it's positive.
I define my lambdas as positive.
It's the lowest.
I said it's the lowest magnitude. I only, lambda, because why do I like negative numbers? Who likes negative numbers?
You say.
Lambda, I think of lambda as being a positive number because that's what I do. All right. So for large z, the EVS CDF, the extreme value statistic CDF, which is G, has a very similar structure, in fact, to the EVS for n IID variables, Gn, that we were discussing in the first part of the talk, right? Where the only difference is here, what do we have here? We have, instead of n, we have t, and instead of here, we had this log g, right? Now we have, instead of log g, we have lambda naught. It's the only difference. Right? And they both decay like a Gaussian for large z, right? So the immediate consequence of all of this is, since we have the EVS behaves as if it was coming from independent variables whose distribution, whose cumulative log of cumulative distribution function is lambda for large times. And so the consequence is first of all, that it does approach Gumbel. So if you're worried about Gumbel, you don't have to worry. You can go to sleep at night knowing the Gumbel is safe. All right. And now there's only one small little problem. And that problem cost me a half a year of my life. Us a half a year of our lives. Lambda naught goes like e to the minus z squared root 2 times z. Log g, for Gaussian random numbers, we showed, went like e to the minus z squared root 2 divided by z. All right? Now, that's a tiny difference. It doesn't change the fact that both are Gumbel, but there's a huge factor, because z is large, of z squared between the two answers. And now, That's a little weird. So in fact, you can make it even weirder. If you think about it, a more general problem. Let's put it in the framework of, instead of looking at the continuous time series, which Majunder is talking about, we take that same time series, but we close our eyes and we only open our eyes once every millisecond. Right? So we don't see everything because we can't see everything. And now, instead of, if we closed our eyes and only looked, say, every hour, and if the time, say, the time constant was a second, well, each number is independent. So if I wait an hour, the system is forgotten what was before, and I have IID variables. If I look every nanosecond, then I have the continuous time series, essentially. But one of them has a z upstairs, and the other has a z downstairs. So what happens in the middle? Something has to happen. So you can imagine that that there's a z to the beta, and that beta is a function of delta. That would be one answer, right? Or, there could be a critical value of delta such that for delta less than 1, it's z upstairs, and for then the phase transition, and for delta less than 1, it's for delta greater than 1, it's downstairs or something like that. Something has to happen. And the question is, what is it? All right. Of such deep questions, they prevent you from sleeping at night and make you work on physics problems. So how do we approach this problem? So we can, first of all, we can construct the map that corresponds to what it means to just periodically sample the Ornstein-Uhlenbeck process. Because there's an exact solution to the Ornstein-Uhlenbeck process for finite times. It's the following map. Xn plus 1 is xn e to the minus delta. That's the forgetting, right? And plus the noise. And it has, okay, and the distribution of the noise is Gaussian, as it should be. And now from that map, so we now change the problem from a Langevin equation to a map, right? And now the master equation, instead of being a differential equation, is a integral equation. You can write down an integral equation. The master equation for the process itself satisfies that equation. That's like the Fokker-Planck equation. That the probability of getting an x is, I start out at some other x prime. I have this amount of Gaussian noise, and that gives me my number, where I have the forgetting factor mu, which is e to the minus delta. Now, in the continuum case, we had to reject all the paths that cross z. That's how we got the EVS problem, the extreme value problem. All right, so we have to do the same thing. We have to put, we only allow P only exists up to z, and we have to throw out anything that went over z. All right, so now that is the integral equation, which is now the same equation that we had, the exact parallel in the discrete case of Majunder's Fokker-Planck equation. All right, so we have this integral operator instead of a Fokker-Planck equation. All right, and all we need is the lowest eigenvalue of that, and we're done. Right, that's what did Majunder did. He found the lowest eigenvalue, the lowest magnitude eigenvalue. We have to do the same thing, and we're done. Now, for Mr. Majunder, to find the lowest eigenvalue of his equation was trivial because it's basically a harmonic oscillator. But the problem is a harmonic oscillator with a wall. It's a parabolic cylinder function, and you're all done. It takes about 2 minutes, 4 minutes, 5 minutes. For Majunder, about 20 seconds. Unfortunately, we have a much harder problem. We have this integral operator. You can't look it up. Not as far as I know. So we got to do it ourselves. So you can, first of all, you can solve it numerically. You just put that down a grid, you put down P, you put it in here, you integrate you iterate that equation until it converges, and that works, and you can get data. So this is what it looks like. This is log of 1 minus lambda time, which is essentially Gaussian, times e to the z squared over 2 to get rid of the Gaussian, which is always that Gaussian factor, right? And now this is for different values of delta, which is mu, because mu is e to the minus delta. So we have our numerical values, and this line here, this dotted line, is the delta equals infinity case. That is the IID case. When delta goes to infinity, it's IID. And what you see is that for large Z, everything is clumping onto the IID. So you ask, what's happening? And the answer is that it seems to be that independent of the value of delta, for all these values of delta, it's always going, for large Z, is always going to the IID limit. That's what seems from the numerics. All right, and you can see that if you look at the distribution itself. So we actually measured the distribution for some particular case, for keeping delta fixed at 0.01, 0.1, so it's a small number. If you look at 100 samples, so it's a short time, then the Rajumdar prediction is this red line. That's the continuous thing. The IID prediction would be that. This is the true, the black line is the true answer. You see that the delta equals 0 limit is much closer to the truth. But now all I do is take the same delta and make time bigger. So instead of looking at 100 samples, I look at 10,000 samples. And now, in fact, the IID prediction is closer. And if I go and look at a million samples, it's even better. And the Rajumdar prediction is getting worse and worse. For the same delta, all I'm doing is taking a longer time series. So as I take the time series longer, Mr. Rajumdar gets worse and worse, and its IID gets better and better. So, all right, now we're running out of time here. When did I actually start? Because we started late. So anybody have? Yeah. All right. So I will try to just give you the flavor of the calculation because you can't do the calculation in front of you. But what's amusing is you can map this problem to a problem of quantum mechanics. And that's beautiful. So we have our problem, and all we're going to do is exactly what we're going to do is take our integral equation and project everything onto the eigenfunctions of the unconstrained Fokker-Planck equation, of the unconstrained, Fokker-Planck equation, which are just Hermite, the eigenvalues are Hermite polynomials times Gaussians, and the eigenvalues are 1, n plus a half. You break the kernel up into that. You you expand P also in terms of these eigenfunctions, and then our beautiful integral equation becomes a matrix equation for an eigenvalue lambda. Our eigenvalue lambda times some vector is a 0th order Hamiltonian, because it's a symmetric matrix, so I can think of it as a Hamiltonian, plus another symmetric matrix, which is our perturbation, times that vector. So what we have now, we've mapped the problem from an integral equation to a matrix equation, right? So it's basically now just perturbation theory and quantum mechanics, which we all know, right? That's why we're physicists, so we know that kind of stuff, right? So the 0th order Hamiltonian is diagonal, and the eigenvalues of the 0th order Hamiltonian are just e to the minus lambda and delta. These are the eigenvalues of the Fokker-Planck equation. The interaction Hamiltonian involves overlaps between eigenfunctions, the nth eigenfunction integrated from 0 to infinity. All right. And now the point is that when z is big, this integral is small. So it's perturbation theory. So all I have to do is do perturbation theory, right? So the 0th order thing is we're looking at the change. I'm working on. The 0th order answer is 1. The next order answer is we take our interaction Hamiltonian, sandwich it between the ground state, we get our Earth C. This plus that is the IID answer. Then the next answer, the non-trivial part, is that it's just a sum with the energy denominators. You do the thing, you get a sum, you work it, which is a beautiful sum with involving Hermite polynomials, and you do the asymptotics, and what you find in the end of the day is that lambda is 1 minus our friend, the IID answer with a correction. And that correction is a function of this variable c, which is defined that delta is c squared over z squared. It's a small number. And so you get that. And now you can also expand in the small delta limit. I don't have time to talk about it. And so in the end of the day, what you find out is that you got a crossover behavior. That you always go large, and for large enough z, large enough times, you always go over to IID. And for small times, it looks like for large times, which are below this z squared over this number, it looks like Mr. Majumdar, and you always cross over to the IID. And we're getting there, okay. And now why does this work? And then down will be the question is what's going on? And the answer is very simple. Here's our update equation. It's for small delta, right? Because there are two pieces. There's the deterministic piece, right, which is the force, and then there's a random piece, which is the noise. And the point is, the random piece scales like square root delta, and the deterministic contribution scales like delta. So when delta is small, who wins? The random piece. All right. And however, when time gets bigger and bigger, the force gets bigger and bigger. And therefore, no matter what the value of delta, if z is big enough, then the force is big, and that dominates. So for any fixed delta, no matter if you wait long enough, you always go over to IAD because the force dominates, and that's the crossover is exactly when these two terms are the same order, and that all works. And so in fact, this works in general for any force. You can, for all forces, there's this crossover as long as the force grows faster than grows with z. And so you can, it works for all kinds of different forces. And so now our conclusions. So what we find is that for all potentials, for all forces that grow at infinity, so the potentials are superlinear, the long time behavior is always that exactly of the IID variables. So the correlations make no difference whatsoever for a long time, if you have a long enough time, which is an amazing thing. For sublinear potentials, it's not, and we don't know exactly what happens. It's always asymptotically Gumbel. What about Mr. Frichet and Mr. Bible? Well, it depends. The answer is it depends, because you have to specify the dynamical process that gets you there, and there are various different kinds of dynamic processes which generate Frichet and Bible equilibrium distributions, depending, and it seems to depend on exactly what problem you're talking about, what the answer is going to be. We don't know, but that's work to the future. And with that, I'm going to conclude. So thank you very much, and take questions.
Just open the chat to see if there are questions for people.
Chat. All right, hold on a second. That requires work. Zoom.
Okay, guys. Thank you very much again, David. And questions from the audience.
Yeah. I'm very much impressed by your deep regard to your audience, for your appreciation of the abilities of your audience to follow you.
I detect this hidden criticism there.
But anyway, so the question is the following. So you have this harmonic line potential, right? And basically, but when you look at extreme values,
right,
then you look at regions which are somehow almost unaffected by it, right?
No. The point is that the extreme values are always when the force is large.
Yes.
That's the whole point. If the force doesn't increase with distance, then you're exactly right. But that's the whole. That's the non-trivial part.
Why is it? Why are they independent?
Because you forget fast. The force is so big.
Oh, so it kills the correlation. It's
right.
like basically mean fields of thing, for this kind of interactions, etc.
Right.
Okay.
I have two basic questions.
Yeah.
One in the dynamical case or the correlated case, when you say there is a T and a capital N both, it is like you evolve the distribution till a time T and then sample.
Right. Exactly. Right. So it's allowed. The point is, it's allowed to leave as long as it comes back in time, and you don't see it. So you only. That's the whole point. Is when you have the difference between the continuum time thing is that if you think about it, if I reach the new maximum today, right, the next number that I'm going to draw, if delta is small, there's a 50% chance that's bigger and a 50% chance that it's smaller. So I'm most likely to get even a bigger number next time. And then when I have a finite delta and with the force, I forget. So all that hard work that went into getting a large number is completely lost. And the only thing that matters is just how many numbers I draw, because I need a big number.
And one more basic question. In the Hamiltonian language, will the crossover look like this, that the lowest eigenvalue or the lowest distribution corresponding to the...
So what lambda, the thing you're looking at is this lambda, which is the eigenvalue itself. And it has a Gaussian piece, which is always there. And the point is that it looks like Z, it looks like Z e to the minus Z squared, right? And then, but at large values of Z, it looks like 1 over Z e to the minus Z squared. So it goes up and then goes down. If you take out the Gaussian, it goes up at the beginning and then goes down at the end. That was this crossover function. But you always cross over to the 1 over Z eventually.
Last question, because we need this rule. So, Jonathan?
Can you add another term to the equation, to the numerical equation that would compete with the force and keep the memory, like non-linearity or something like that?
That's a question that's way too deep. Over lunch or something.
All right, so thank you very much again, David. Happy moving and see you all next week.
Yeah. And now I have to close the Zoom. Wait, we'll just and stop share.
Sure. When you have the recording, please send it to me. So post it.